And there is a tie. Compare the MAC head.
So for the root bridge and this STP network will be which tree?
Those are the two components of the spanning tree bridge ID. And the switch with the lowest bridge ID becomes the root bridge. In this case, the answer is fairly obvious. Switch tree has the lowest priority, 2, 4, 5, 7, 6. So it will be the root bridge. So we now know the port role of each interface on switch tree. All of its interfaces must be designated ports, because it is the root bridge. Just to make things easier to remember, let me make labels. Click on the note button up here, and let me make 4 Ds for designated. Okay, and after we have made them, let's move them into position. Okay, so all 4 interfaces on switch 3 are designated ports. Next up, let's find the root ports. Each other switch into the port.
The root will be 0403.
OG.
03 in F0
must have a single root port. The first criteria to determine the root port is the root cost. The interface with the lowest root cost will become the root port. How about switch 1? Via either X01 or X02, it would have a cost of 19, plus 4 for switch 1's G01, and plus 4 for switch 4's G02. So 27. Via X03 or X04, it has a cost of just 19. So the root port will be either X03 or X04, but we don't know which. It would have the first criteria to determine the root port is the root cost. The interface with the lowest root cost will become the root port. How about switch 1? Via either X01 or X02, it would have a cost of 19, plus 4 for switch 1's G01, and plus 4 for switch 4's G02. So 27. Via X03 or X04, it has a cost of just 19. So the root port will be either X03 or X04, but we don't know which, so let's look at the tiebreaker.
Ngerti kontol.
Sabar. Ada lunok sih, Bang. OTW paling kencang.
But with STP. But let's redundant network went down for an hour. That would certainly be bad for them. Take over with little or no downtime. Finally, as much as possible, must implement redundancy at every possible point. There are many points of failure here. Hardware failure. This entire network loses connectivity to the internet. Or, if this connection is cut off due to a hardware failure, these hosts lose connectivity within the LAN and out to the internet. Okay, those are just 2 examples. Let's look at a better network design. This network here is a much better design. If this PC wants to reach the internet, it might use this path in a normal situation. However, even if this router has a hardware failure and goes down completely, the PC can reach the internet via this or another alternate path. Perhaps traffic to this other PC in the LAN usually follows this path to the destination. What if this switch fails? That's not a problem, because this alternate path is available. So, I think you can see the benefit of designing redundant networks. However, you may be asking, this switch fails. Well, if that is the case, all hosts connected to this switch would lose connectivity. Unfortunately, most PCs only have a single network interface card, NIC, so they can only be plugged into a single switch. However, important servers typically have multiple NICs, so they can be plugged into multiple switches for redundancy. We will cover many protocols that are used to enable network redundancy throughout this course. and spanning tree is one of them. Spanning tree is a layer 2 protocol. It enables redundant layer 2 networks. So within the LAN here, not routing out to the internet between networks at layer 3. I just showed you the benefits of a redundant LAN. Having multiple paths between these switches provides alternate paths if one connection fails. However, without spanning tree, there is a major problem here which can destroy your network. So, where is the problem? Let me introduce the concept of broadcast storms. I'll use a simplified network topology to demonstrate the issue. PC1 is 10.0.0.1, PC2 is 10.0.0.2, and PC3 is 10.0.0.3. You already know what a switch does with a broadcast frame or an unknown unicast frame. Let's say, for example, PC1 wants to send some traffic to PC2. To do that, it needs to know PC2's MAC address. So let's say PC1 sends an ARP request frame, which is a broadcast frame. It uses the broadcast MAC address of all Fs as its layer 2 address. When switch 1 receives the frame, what will it do? As I said, you already know what a switch does with broadcast and unknown unicast frame. It will flood it out of all interfaces, except the one it was received on. So switch 2 and switch 3 both receive a copy of the frame. They then do the same thing. They flood it out all interfaces, except the one it was received on. So PC2 receives the ARP request and will reply with a unicast ARP reply. All good? Actually, no, not all good. Although PC2 received the ARP request and sent its reply, these broadcast frames still remain on the network. I've cleaned up the arrows so you can see this easier. As I just said, PC2 received the ARP request and sent the reply. But what about these broadcast frames in the network? The switches will continue flooding them. So what will happen after this? Switch 1 just received 2 broadcast frames on 2 different interfaces. It will once again flood them. Let me clean that up again. Switch 2 and switch 3 both just received broadcast frames. What will they do? They will flood them. So I think you get the point. This will continue forever. Do you remember the TTL, or time to live field of the IP header? It is used to prevent infinite loops at layer 3. It will switch 1 just received 2 broadcast frames on 2 different interfaces. It will once again flood them. Let me clean that up again. Switch 2 and switch 3 both just received broadcast frames. What will they do? They will flood them. So I think you get the point. This will continue forever. Do you remember the TTL, or time to live field of the IP header? It is used to prevent infinite loops at layer 3. But the Ethernet header doesn't have a TTL field. These broadcast frames will loop around the network indefinitely. If enough of these looped broadcasts accumulate in the network will be too congested for legitimate traffic to use the network. This is called a broadcast storm. Eventually, your network will look like this, so full of looping broadcast frames that no regular traffic can pass through your network. The red arrows represent the clockwise loop, between the 3 switches, and the purple arrows, the counterclockwise loop. However, the red arrows represent the clockwise loop between the 3 switches, and the purple arrows, the counterclockwise loop. However, network congestion isn't the only problem. Each time a frame arrives on a switch port, the switch uses the source MAC address field to learn the MAC address and update its MAC address table. When the frames with the same source MAC address repeatedly arrive on different interfaces, the switch is continuously updating the interface in its MAC address table. This is known as MAC address flapping. So how can we design a network with redundant paths that doesn't result in layer 2 loops? Well, spanning tree protocol is one answer to this problem. So let's take a look at spanning tree protocol. What we now call classic spanning tree protocol is an industry standard protocol, IEEE 802.1d. This is the type of STP we will focus on in today's video. We will focus on the newer rapid STP later. Because it is so important to prevent layer 2 loops, switches from all vendors run STP by default. So you won't only find STP on Cisco switches. STP prevents layer 2 loops by placing redundant ports in a blocking state, essentially disabling the interface. These interfaces act as backups that can enter a forwarding state if an active interface, meaning an interface that is currently forwarding, fails. Interfaces in a forwarding state behave normally. They send and receive all normal traffic. However, interfaces in a blocking state only send or receive STP messages called BPDUs, or Bridge Protocol Data Units, and some other specific traffic. Before going more in depth, let me talk about that word bridge. I told you about Ethernet hubs in a previous video. Hubs were used before switches were invented, and instead of learning MAC addresses to forward frames to the correct destination, they simply flooded frames out of all interfaces. But actually, before switches, there was another kind of device called a bridge. You don't need to know about bridges for the CCNA. They are an old technology, but they're like a transitional stage between the hub and the switch. However, the reason I'm telling you about bridges is that spanning tree protocol still uses the term bridge. However, when we use the term bridge, we really mean switch. Bridges are not used in modern networks. So in this lecture, and really anytime I talk about STP, you'll hear me use the term bridge, but really it means switch. So if we look at this topology again, perhaps these interfaces are in a forwarding state, while this one on switch 3 is in a blocking state, effectively disabling the connection between switch 2 and switch 3. So effectively, it's like that link doesn't exist, and this is our topology. If PC1 sends that same ARP request broadcast frame, it will be flooded like this, no more loops. However, if at some point another interface fails, perhaps this one, the switches will automatically adjust the topology, and the broadcast frame will be flooded like this, again, no loops. So that is just a basic outline of the purpose of spanning tree protocol. Now let's go a little deeper into how spanning tree protocol works. By selecting which ports are forwarding and which ports are blocking, STP creates a single path to and from each point in the network. This prevents layer 2 loops. There is a set process that STP uses to determine which ports should be forwarding and which should be blocking. That process is what we will cover next. STP-enabled switches send hello BPDUs out of all interfaces. The default timer is 2 seconds. So the switch will send a hello BPDU out of every interface, once every 2 seconds. If a switch receives a hello BPDU on an interface, it knows that interface is connected to another switch, because routers, PCs, and such do not use STP, so they do not send hello BPDUs. So back to our topology here. These switches will send BPDUs out of each interface to our topology here. That's the hello BPDU on an interface. It knows that interface is connected to another switch.
If a switch receives a hello BPDU interface, it knows that interface is connected to a switch. Others, PCs, etc. do not use STP, so they do not send hello BPDU.
Because routers, PCs, and such do not use STP, so they do not send hello BPDUs. So back to our topology here. These switches will send BPDUs out of each interface like this. They use these BPDUs to advertise themselves to other switches and to learn about other switches. Now, what exactly are these BPDUs used for? First of all, switches use one field in the STP BPDU, the bridge ID field, to elect a root bridge for the network. The switch with the lowest bridge ID becomes the root bridge. I'll talk about the bridge ID in the next slide. All ports on the root bridge are put in a forwarding state, and other switches in the topology must have a path to reach the root bridge. So, as I mentioned previously, STP puts ports in either a blocking or forwarding state to avoid layer 2 loops in the network. However, as I just said, on the root bridge, all ports are forwarding, and all other switches must have a path to reach the root bridge. Traditionally, the bridge ID field of the spanning tree BPDU looked like this. There is a bridge priority field, which is 16 bits in length, and then there is the MAC address of the switch, which, as you already know, is 48 bits in length. The default bridge priority is 32768 on all switches, so by default, the MAC address is used as the tiebreaker. As I said before, the switch with the lowest bridge ID becomes the root bridge. So therefore, by default, the switch with the lowest MAC address becomes the root bridge. So here's that topology once again. And I've written the priority and MAC address for each switch. As you know, MAC addresses are 12 hexadecimal digits, but I've shortened them to 3. I've also added port lights for the interfaces to show if they are forwarding or blocking. The G02 interface on each switch is connected to a PC. So because it isn't receiving any BPDUs, it knows it is safe to go into forwarding mode. There's no risk of creating a layer 2 loop. So these port lights are all green. Now, all 3 switches have the default priority of 32768. So in order to know which one will be the root bridge, you will have to compare the MAC addresses. Remember, the lowest bridge ID wins. Which of these MAC addresses is the lowest?
Which one?
Well, hexadecimal A is equal to 10, B is equal to 11, and C is equal to 12. So, switch 1 has the lowest MAC address. Therefore, switch 1 will become the root bridge of this network. All ports on the root bridge become designated ports in a forwarding state. So, that is the traditional bridge ID. However, the bridge ID was actually updated to look like this. In reality, the bridge priority has been updated to be made of 2 parts. The bridge priority, which is 4 bits, and the extended system ID, which is just the VLAN ID, which is 12 bits. Because, as you know, a VLAN number is 12 bits in length. Why include a VLAN ID in the bridge priority? Well, Cisco switches use a version of STP called PVST, which stands for Per VLAN Spanning Tree. PVST runs a separate STP instance in each VLAN. So in each VLAN, different interfaces can be forwarding or blocking. One interface could be forwarding VLAN 1, but blocking in VLAN 2, for example. By adding the VLAN ID into the bridge priority, the switch will have a different bridge ID in each VLAN. Here's a deeper look at the bridge priority field. You may have wondered why 32768 is the default bridge priority. Well, it's because this total field is 16 bits in length, and the most significant bit is set to 1 by default. Therefore, the bridge priority was 32768. However, with the addition of the extended system ID, adding the VLAN ID number to the bridge priority, that changed. So the default VLAN ID is 1, therefore the bridge priority in total actually isn't 32768, it's 32769. In the default VLAN of 1, the default bridge priority is actually 32769, which is 32768 plus 1. Now here's a question. If you want to increase the switch's bridge priority without changing VLAN numbers, what is the minimum unit of increase or decrease? Let me explain what I mean in the next slide. The bridge priority plus extended system ID is a single field of the bridge ID. However, the extended system ID is set and cannot be changed because it is determined by the VLAN. Therefore, we can only change the total bridge priority, that is the bridge priority plus extended system ID, in units of 4096, the value of the least significant bit of the bridge priority portion. Let me demonstrate. Currently, the bridge priority here is 32769. Let's reduce it to make this switch the root bridge. If I want to reduce it just a little, I can reduce it to 28673, which is 16,384 plus 8,192 plus 4,096 plus 1. I could reduce it more, of course, but the point is this. The STP bridge priority can only be changed in units of 4,096. So the valid values you can configure are listed here, starting from 0 and increasing in units of 4,096. The extended system ID will then be added to this number to make the total bridge priority value. So let's look at this topology again. We'll just be looking at the STP topology for a single VLAN, VLAN 1. So the priority for each switch is 32769. But if there are multiple VLANs, say VLAN 1, VLAN 2, and VLAN 3 in this network, the priority would be 32770 for VLAN 2 and 32771 for VLAN 3, etc. We could also change the bridge priority on the switches for a specific VLAN. So, for example, switch 1 is the root bridge for VLAN 1, switch 2 could be the root bridge in VLAN 2, and switch 3 could be the root bridge in VLAN 3. I'll talk about how you can do that in the next video. I just want to let you know some of the possibilities. So here in VLAN 1, switch 1 is the root bridge. All interfaces on the root bridge are designated ports, and designated ports are in a forwarding state. Designated port is just one of the port roles in Spanish. There are a couple other port roles. I will introduce those in a minute. Okay, just a few more points about the root bridge. When a switch is powered on, it assumes it is the root bridge. It will only give up its position if it receives a superior BPDU. And superior means a BPDU from a switch with a lower bridge ID. Once the topology has converged, and all switches agree on the root bridge, only the root bridge sends BPDUs. The reason all switches send BPDUs at first is because they all think they are the root bridge. Other switches in the network will forward BPDUs from the root bridge, but they will not generate their own original BPDUs. Before moving on, let's see if you understand by doing a few practice questions. In this network of 4 switches, which will become the root bridge? Pause the video now to think about the answer.
Which 3 will be the root bridge?
Okay, did you find the root bridge? The answer is switch 3. Both switch 1 and switch 3 have the same priority, 12289. But switch 3's MAC address is lower. The first half, 014A38, is the same, but the next digit is F for switch 1, but 2 for switch 3. So switch 3's MAC address is lower. Let's do another practice question. Okay, here it is. Which switch will become the root bridge in this case?
Which 4?
Pause the video to think about your answer.
Maybe I don't like it, but I have no
Okay, the answer is
choice.
switch 4. It has the lowest priority of the 4 switches, 4,097. Okay, let's move on. So far, we have covered the first step of spanning tree's process of creating loop-free layer 2 LANs. Step 1. The switch with the lowest bridge ID is elected as the root bridge. All ports on the root bridge are designated ports, so they are in a forwarding state. It's important that this is the first step that spanning tree takes, because the rest of the steps depend on knowing which switch is the loop-free layer 2 LANs. Step 1. The switch with the lowest bridge ID is elected as the root bridge. All ports on the root bridge are designated ports, so they are in a forwarding state. It's important that this is the first step that spanning tree takes, because the rest of the steps depend on knowing which switch is the root bridge. Now let's go on to step 2. All other switches will select one of its ports to be its root port. So that means there is one.
Each remaining switch will select one of its interface to be its root port. The interface with the lowest root cost will be the root port. Root ports are also in forwarding state.
Root port on each switch in the network, except on the root bridge. The interface with the lowest root cost will be the root port.
Pernah ketemu
Root
Imo,
ports are also in a forwarding state.
kawannya
Now
itu.
let's talk about what that root cost
Tadi
is.
Imo kelakuannya kayak Honda.
Each interface has an associated spanning tree cost. A regular Ethernet interface with a speed of 10 megabits per second has a cost of 100.
Diapain?
Fast Ethernet, 100 megabits per second, has a cost of 19.
Temen gue tuh.
Gigabit Ethernet has a cost of 4, and 10 gigabit Ethernet has a cost of 2. Make sure you remember these path costs for the exam. Of course, there will be flashcards in the deck for this video, so use those to help you remember. So these are gigabit Ethernet ports, so they all have a cost of 4. The root cost is the total cost of the outgoing interfaces along the path to the root bridge. Which one is the root bridge?
Parah biru linknya.
So these are gigabit Ethernet ports, so they all have a cost of 4. The root cost is the total cost of the outgoing interfaces along the path to the root bridge. Which one is the root bridge?
Dikasih
So it has a cost of
dikasih
0
bayangan.
on all interfaces. They are gigabit Ethernet interfaces,
Dur.
but you don't count the cost of the
Ya,
receiving.
Cudar. Kontek. Ya. Cupu anjing Ray. Raai. Anjing Pak Witanya 4.000.